Hello and welcome to QuantumLeaps. In this video, I'd like to show you how to use the QP Real-Time Embedded Framework with the STM32Cube IDE. This will allow you to apply modern embedded programming with active objects, hierarchical state machines, modeling, and powerful software tracing in this popular STM32 development environment. The plan for today is to start with a blank STM32Cube IDE and create an STM32 project from scratch, showing you all the steps necessary to make it into a working QP application. However, from the start you should know that the complete project is also available for download from the QuantumLeaps GitHub repository qpc-examples. The link is provided in the video description below. To start, click on Create a new STM32 project. You will be prompted to specify either just the microcontroller or the whole board. For this tutorial, I've chosen the Nucleo U545RE-Q board with the Cortex M33 CPU. To select it, click on the Board Selector tab and start typing Nucleo-U545. Choose Nucleo U545RE-Q from the drop-down. Once you've selected the board, click Next to proceed. Now, let's name the new project Project, and put it in the newly created directory DPP Nucleo U545RE QK Cube, because it will contain the standard QP Dining Philosophy Problem DPP application with the preemptive QK kernel. For the initialize peripherals, click No. Now you are almost ready to generate the code from these settings, but the default based on the HAL, which stands for the Hardware Abstraction Layer, is quite bloated. To reduce the overhead, you can choose the lower-level code generation by clicking on My Project tab and selecting the Advanced section. You generate the code by clicking on the Generate Code button in the top toolbar. As usual with Eclipse-based tools like STM32Cube, it's a good idea to monitor what's happening on the disk, because the project includes everything on it, whether you want it or not. Now you can build the code by pressing the Hammer tool in the top toolbar. The build should succeed and should create the debug directory on the disk. Alright, time to connect the Nucleo U545 board to your computer and debug the code by pressing the Bug tool in the top toolbar. You can step through the code up to the obligatory while one super loop, but the super loop is empty, so the code runs, but nothing really happens. To make the code do something, let's insert the usual blinky code, which turns the onboard LED on, attached to the GPIO-A pin 5, delays for a number of milliseconds, turns the LED off, and delays again. As you can see, the onboard LED is turned on and off, and blinks when you run the program free without any breakpoints. Alright, so now that the basic blinky is working, you can start making it into a QP-based application. The first step is to add the QuantumLeaps QP framework as an embedded software package. Select the menu Help, Manage Embedded Software Packages. In my setup, QuantumLeaps is already listed, but in your STM32Cube it will be missing and you need to add it. There are a couple of ways to do this, but perhaps the best option is to add QuantumLeaps from the URL. After clicking New, you are prompted to enter the URL. To find out the URL of the QuantumLeaps package index, go to the QuantumLeaps GitHub page and find the cmsis-packs repository. Here, click on the QuantumLeaps.pix file, and then click on the raw view. Copy that link, paste it into the STM32 message box, and click Check. It should be fine, so click OK. Click OK again and wait until the package index refreshes. At this point, QuantumLeaps should appear in your package manager. Expand the QPC section and tick the box for the latest version at the top. Click Install and accept the licensing terms. In case you are wondering where Cube has put the package, you can find it in the user directory STM32Cube repository packs folder. Anyway, the next step is to select the QPC framework components and add them to your project. To do that, you need to double-click on the MX file project.ioc. This opens the CubeMX perspective, where you click on the Software Packs menu and then on Select Components. Here you should see QuantumLeaps.qpc. Expand it and then expand the Real-Time Embedded Framework section as well. From the drop-down menu, select Event Processor QEP, Framework QF, Software Tracing QS, and finally Real-Time Kernel. The kernel section offers several selections like the QV kernel, QK kernel, QXK kernel, and a number of third-party RTOS kernels. For now, select QK, which is a preemptive non-blocking kernel. The next step is to add the just selected QPC components to the project. To do that, expand the Middleware and Software Packs section and scroll down to QPC. Now expand the Deceptively Hidden panel to the right. Click on QPC and notice the appearing option under the Mode section. Tick the box next to RTEF QPC. At this point, you can regenerate the code. You can also check your project on disk and notice the new subdirectory Middlewares, which now contains the QPC framework. Let's try to build what you've got so far. There are, of course, some errors. The first class of errors concerns the QS software tracing, which has been selected but should not be used in the currently active debug build configuration. To fix this, you need to exclude the QS source code from the current build. Right-click on the QS subdirectory and choose Properties from the bottom of the drop-down menu. In the Properties dialog box, click on the C++ build section, and then tick the box next to Exclude Resource from Build. Notice that this is only for the currently active debug build. Notice that the QS subdirectory now appears crossed over. Alright, next build attempt. This time, compilation errors are gone, but there are a couple of linking errors about the multiply defined PNSV handler and NMI handler. Indeed, these ARM Cortex-M exceptions are used inside the preemptive QK kernel, so they should not be generated by CubeMX. To turn off the generation of the exception handlers, open the CubeMX perspective by clicking on the project.ioc file. Next, expand the System Core section and click on NVIC. As you can see, the standard exceptions are enabled and you cannot change that. But click on the Code Generation tab, where you can deselect code generation for the non-maskable interrupt and for the pendable request for system services. Regenerate the code and try to build it again. The last linker errors are about the missing QOnError function, which is the error handler for the QPC framework. In the standard QPC examples, the QOnError function is defined inside the BSP, the board support package. So let's go to the standard QPC examples. ARM Cortex-M, DPP on Nucleo U545, QK kernel, and open bsp.c. Find the QOnError function and copy it. Paste it into your main.c file, but be careful to place it inside the user section, which is preserved during code regeneration. Before building, remove the code that does not match the context of main.c. Now, the compiler does not like the signature of Q on error, so you need to include the qpc.h header file, again carefully inside a user section. Okay, so the code builds cleanly, but it will still only blink the LED as before because the main function does not actually call any QP services. So now you need to add a QP application. For this example, you can take the standard DPP application. You could take just the source code consisting of dpp.h, philo.c, and table.c to your STM32Cube project directory. But this code, which by the way is completely independent on the target board and is actually the same in all DPP examples, has been generated by the QM modeling tool. So instead of the generated files, you can just download the QM model and generate the code locally. Regarding where to save the model inside your Cube project, you can put it in the core directory. Apart from the application, you need the BSP code. The bsp.h header file is the same for all DPP applications, and you can save it in your core inc directory. However, the bsp.c implementation depends on the board and the real-time kernel, so you need to take it from the specific example for your current board and the QK kernel in this case. You can put it in the src directory. After adding the application, let's build to refresh the Project Explorer view. The compiler complains now about the dpp.h file missing because we haven't actually generated the code from the QM model yet. So let's fix it right away by double-clicking on the dpp.qm model file. This opens the QM modeling tool, which I presume you have installed. The DPP model currently generates the code in the dot directory, which is relative to the model file and means the same directory as the model. This wouldn't quite match the structure imposed by the STM32Cube, but you can easily adjust it. Rename the dot directory to inc, again relative to the model file. Also, add another directory and name it src. Now move philo.c and table.c into the new src directory. Finally, generate the code from thus modified file. You can check on disk that the dpp.h file has been generated in the core inc directory and philo.c and table.c in the core src directory. When you build the project now, you have a couple of linker errors. The Q on error is multiply defined because it is now both in main.c and in bsp.c. Let's remove the definition from main.c. The other problem is the multiply defined sysdig handler because it is generated by qpmx and is also defined in the bsp.c file. By now you should know how to fix it by opening the qpmx perspective and disabling sysdig generation in the envix section. Finally, the project builds cleanly, but the main function still does not call any QP services. So the final touch is to add the correct calls. For that, go to the standard qpc-examples and see the main.c file. Copy the guts of the main function and paste it into your main.c right before the while1 superloop. Please note that qfrun does not return, so the superloop downstream won't execute. The last minor issue is the missing signatures of the BSP functions, for which you need to include bsp.h. And finally, the project builds cleanly, and I'm sure you are curious whether it runs. Start the debugger and first let the code run free. Watch the activity on the onboard LED. When you break into the running code, you find it in the qk-on-idle callback, which is precisely what you expect. So congratulations, you have just implemented your first QP application with STM32Cube. For wrapping up this video, I'd like to point out a few aspects you might consider. First, regarding bsp.c, it was taken from a standalone example, but in a Cube project you might remove the initializations and other elements already provided in main.c by cubemx. For example, instead of the specific STM32 include, you can include main.h. This header file already defines a bunch of macros, which you can delete from bsp.c. Another aspect is the compile time configuration of the QP framework, which is managed by the qp_config.h header file. It is located in the QPC framework in the directory ports, armcm, qk, config, because the specific configuration depends on the real-time kernel type. The qp-config header file is documented in the QPC manual. It allows you to fine-tune the framework for the specific application. The file uses the cmsis-specified formatting that some tools like Kyle Microvision, for example, can display as a dialog box. The Cube IDE doesn't seem to have this option though. But anyway, the important thing is that qp-config is used only when the macro qp_config is specified to the compiler, so you might want to add it like this. Another aspect worth considering is the integration between the error handling in Cube and in QP. Specifically, the hull error handler should not enter the while-1 loop because this represents denial of service. Instead, error handler should call QOnError. Also, assert handler should do the same, remembering that QOnError must be called with interrupts disabled. Similar arguments apply to the exception handlers defined in the file stm32_it.c. Here again, you should avoid denial of service, and instead you should disable interrupts and call QOnError. With this, I'd like to conclude this video. You have seen how to work with QP in Cube, but you still need to see how to integrate the powerful QP-SPY software tracing with Cube. This will be the subject of a separate video. Finally, please note that the complete STM32 project just demonstrated is available for download from the QuantumLeaps GitHub repo. Thank you for watching.